Thank you, Sheldon. Geometallurgy is all about leveraging, and whilst machine learning provides the tools, it's domain expertise that drives successful outcomes. Recovery of mineral products from mining operations is governed by, amongst other things, three axioms. Firstly, the whole production chain is dependent on the characteristics of the ore. Secondly, only a tiny fraction of the ore will be tested before it's mined. And thirdly, ore bodies are intrinsically variable. So it follows that mining and ore processing systems are designed and operated in an environment of ore body uncertainty. Simplistically, uncertainty in a mining operation costs money in a couple of ways. Firstly, it leads to incorrect decisions at all scales, from short-term tactical decisions to long-term strategic ones. For example, if we consider a truckload of ore, if the estimated characteristics of the ore are exactly the same as the actual characteristics in the truck, the correct decision about where to send the ore is made every time. But uncertainty in the estimates means predicted and actual are rarely identical, so many trucks will be sent to the wrong destination. This might mean that ore that should go to the heap leach is incorrectly sent to flotation, for example, and these losses are not recoverable. Secondly, uncertainty in the ore body leads to mismatches between plant operating settings and the characteristics of ore feed. Correct settings may continuously lag the presentation of the ore. Again, the losses are not recoverable, and this is true whether we're looking at mill throughput, reagent consumption, power consumption, or mineral recovery. At AMC, we take a broad view that geometallurgy as the integration of geological, geotechnical, mining, metallurgical, environmental, and economic information to provide the key to help maximize the value of an ore body. And as a bonus, it helps to minimize technical and operational risk. The key is that geometallurgy provides a method for obtaining much greater leverage from low-cost data to improve estimates and reduce ore body uncertainty. Metallurgical tests are labor-intensive, slow, and consequently expensive. By contrast, many different types of data can be gathered from drill samples at relatively low cost or for no cost at all. AMC's expert domain knowledge helps our clients to understand what can be collected, how the data should be structured, and how it should be validated. In the pre-production period, the primary source of information about the ore body is likely to come from samples collected from drill holes. We match geological data with metallurgical test data and use data analytics and machine learning to build understanding of relationships and model the response of ore to metallurgical processing. We then leverage those models using the much larger drill hole data set and deploy those predictive relationships across the client's resource block model. This provides a granular map of ore processing response in 3 dimensions, which forms the basis of production schedules, blending and stockpiling plans, and strategic optimization of the project. Data analysis and machine learning provide the tools and the grunt to handle large volumes of multivariate data. Outcomes depend on the understanding of the raw data, and the old adage, garbage in, garbage out, is still relevant in the age of machine learning. Decisions about how to combine different data types, what is an outlier and what is an error, what to leave in and what to exclude, all require geological and metallurgical domain expertise. Once in production, the mine and the plant generate a huge array of data that describes the characteristics of the ore and its processing response under real, full-scale operating conditions. We can now merge data generated in the ore control system in the mine with data generated by the comminution and mineral recovery circuits. Same expert-driven machine learning methods are used to build predictive relationships between ore control data and the plant data. And these are then used to calibrate the pre-mining predictions from the drill sample data and to update the geometallurgical block model. Further benefits may be derived by deploying the predictive algorithms in digital twins. Domain expertise is again crucial to ensure that outcomes from machine learning are built on reliable foundations. So to wrap up, geometallurgy improves the accuracy and granularity of forecasts. It enables better control of ore feed qualities. It reduces unplanned variability in the process plant, and it ultimately improves recoveries and reduces costs. While machine learning provides the tools and the power to handle large multivariate data sets, it is domain expertise ultimately that drives success. Thank you.